in essence, I want to flag that this is a collaboration that involves myself and then CSIRO with at least 3 different areas there. So ocean atmospheres and the AIM FSP, as well as Data 61. There's a role that QUT are playing too, particularly with respect to the some of the ML you'll hear about. But there's also some collaborations which are just starting to commence around the edges of that as well, one of which you'll hear about towards the tail end of the talk. I'm going to, as I said, talk a little bit about the platform, Russ then about COTS surveys and results, and we'll look forward from there. This whole thing really started about 3 and a bit years ago now, when the current round of crown-of-thorns control team work was being bid. And I got to contemplating how to replace the old school sort of manta technique, which is, goes back to Cheshire in '69 and the crown-of-thorns, workshops and surveys. But in essence, it's a broad-scale survey technique that we're going to be talking about here today. It's really not much more than that. But I want to start by saying that one of my passions is I'm a pilot. I fly airplanes. The glider in the center of the screen there is a Schleicher ASW 19. And if you are doing your pixel transformations in your head very well, you'll realize that that's the glider that's in the logo. But the point I want to make is this, that gliders kind of represent the pinnacle of efficiency of flight. They have to, otherwise you hit the dirt a little bit too quickly. They can fly extremely, I must have a timer on here. They must extremely long, high, fast, all the rest of it. But this is because they are very efficient in their flight control surfaces, and they are a proper airplane using ailerons and rudders and elevators and flaps. When you contrast that with the kinds of things that we put in the water, some of them are more appropriately called a brick on a string. And even the ones which are closest in underwater flight rarely use this combination of wings and ailerons and rudders and elevators. And Vertigo3 has been very, very deliberately designed to mimic true flight underwater. So again, wings, ailerons, elevators, rudders, very, very low drag. And when I say that, I'm talking about when it's being towed in an operational sense, relatively shallow, total drag forces of the glider are less than 1 kilogram. This, of course, means that you don't need a big boat and all the rest of it. It also means you can pull them very fast without them putting a lot of drag on. And for a bunch of reasons, it's also very, very maneuverable, but largely autonomous, so that a pilot can sit there and make some control inputs. I want to address this thing of being tied to the boat by a rope, which is a little unusual in some of the underwater stuff. People tend to think that autonomous is sexy. But as soon as you go underwater, of course, you've lost your ability for GPS spatial location. Bandwidth is down to almost nothing, and you have to consume 90-odd% of your energy requirements for moving your underwater body through the water. If you can sort of do away with those things by using a cable, then you can become small and therefore agile and fast. It's a robotic vision-based system, so it's got a 5-megapixel camera in it, very, very deliberately with a oblique downwards view, and very deliberately using video at 15 frames per second. That's not a special number, but the point is it has to be a fast enough frame rate to enable the benefit of tracking objects through a video field. The human eye is great, of course, and very, very good in that central 1 degree or so, around a pretty good out to about 6 degrees. But beyond that, we have to turn our head and scan the horizon or scan our setting to be able to see in that amount of detail. Of course, the robotic vision thing can do it across the entire field of view the entire time. The thing about the oblique camera view is it allows us to see morphology in the far field, as well as vertical views and extents and percentage covers, etc., in the down view portion of the same image plane. It also allows us to do funky things like seeing behind a bommie as the glider flies over it, even without the glider going nose down over a bommy, we actually get, for a brief few frames, a view of the back edge of that bommy. And I guess I wanted to just sort of say that the task of doing vertical projected ML would be kind of analogous to saying, let's do facial rec for people from a camera in the sky that can only see the tops of their head. So accepting that morphology is quite important to us, the whole oblique view thing is quite important. Now, this is a standard view from the glider, kind of gets chucked in the water, boat moves off, very much like a manta toe. The image you see right now, though, is the panoramic view subsetted down to the vertical portion of that screen. So you can see there that even though we're dealing with a relatively small part of that screen, we've got quite a bit of our frame real estate, our image frame real estate in that vertical down thing, which kind of is what, as scientists, we tend to use for percentage cover estimates and things like that. I'm going to hand over to Russ in just a sec to talk about this, but clearly the project arose out of a need to think about becoming efficient with crown-of-thorns culling efforts. Russ was one of the very first guys I reached out to bounce the idea off. Russ, you're unmuted there, so I think over to you.
Okay, thanks, Brett. Yeah, and I just want to say to everybody that it's been great to be part of this work, working with a guy with the imagination that Brett has got, and also with Brano Kusi's team from the AIM-SP, who can bring to bear a lot of those technological and computing skills and that sort of background. I think it's coming together really well, and that's important because we need to be as efficient as we can with trying to control the crown-of-thorns starfish. It's a huge job because the GBR is huge, but also it's difficult in its own right. They're tricky animals to spot and find and kill. So doing it effectively is important, and a lot of progress has been made in that area by incorporating pre-cull surveys as part of the integrated pest management program, but they rely on people in the water. That takes time, and it takes people away from doing the diver control stuff. So as much fun as manta towing may be, and you can see a couple of people manta towing into jaws there in image number 3. It's not potentially the most time-effective way of doing it. And there, this glider, I think, really represents a step forward in that effort. So next, Brett. And here's an example of just what it can do. So in July, our team went up to Capricorn Bunker Group, based out of Heron Island, and we did some manta tows around Fitzroy Reef, Llewellyn Reef, and part of Lamont in the time that we had there. So you can see the perimeter that we towed of Fitzroy. We also did Fitzroy Shoal, which is a kind of extension of the reef that's around 20 to 25 meters deep off of there, below diver depths and below manta tow depths in most cases. So we covered many kilometers of reef there and accumulated a lot of images. Went through those images one by one, mostly Brett and I, putting these red boxes around all the starfish that we could see. So there's a hell of a lot of data there. High resolution images are pretty high anyway these days. So every 66 milliseconds, or 15 times a second, we're picking up these starfish. And in this image, which has been just picked out, there are 4 starfish. So you might see 2 of them pretty much immediately. It takes a bit more work to find the other 2. So here they all are. And this kind of comparison between the previous image and this one just highlights one of the benefits of using computers and machine learning to identify these things. So this image is a lot brighter, and the starfish are clearer because we've tweaked the brightness and contrast. computers don't need to do that. All the information is there and they can still pull it out without any of that fiddling around. So it's just one example of how this can streamline the process. Next. So this is the kind of thing that we found. So here's Fitzroy Reef, and in June, the COTS control team went to this reef to conduct control culling operations. And before they did that, they did what they usually do, which is tow around the perimeter of the reef and find where the starfish are so that they can target their operations. And each of those red dots represents a crown-of-thorns or a sector of reef, a 2-minute manta tow where a crown-of-thorns was seen. And on the right, it's the same data from our tow. And you can see that there's a pretty close correspondence between the data from the manta tow and the data from the glider. And next, just boring down into that result a bit more and contrasting them. One of the differences between the two types of data is that the manta tow kind of unit of resolution is about a 200-meter long stretch of reef. So, you know, that's where the data is reported from. Tow is about 3 knots, and the divers relate back this information to someone in the boat, recording coral cover, live and dead, number of starfish, their size, number of feeding scars, and so on. So with the glider, by contrast, we have a wider and potentially deeper track, depending on where you choose to tow it, but it can go deeper than the manta tow divers. There are more data points because you get a data point, 15 per second, in fact, that can be interrogated. And that really gives you kind of qualitatively different results as can be illustrated by one of these outputs from the images. We go to the next one. So there's on average 1,200 images per 200 meters. We're towing faster, and we get a lot of information, not only about what the machine is doing, but also geolocation, far more precise and accurate location of the starfish. We get environmental data that corresponds to each of those points. We've got an image of everything that we can go back and interrogate later. And we can use machine learning to pull information out of those things once it's been trained. But just to contrast the results again, the blue is the manta tow data from June, and the glider Vertigo3 data in July, less than a month later. So it's very similar. And in fact, despite the control operations, we found more starfish in July than we did in June. So I guess highlights why we need to keep going back to these reefs until the starfish are controlled. Just thinking about the relative efficiency and the amount of information that these methods can provide. The manta tow saw 25 starfish. Brett and I, going through all of those images painstakingly, found 50. Okay, so twice as many. It took a lot of time to go through those images, but when we applied machine learning to those images, we found even more starfish, and that analysis can be done in a matter of a few minutes. So it's about 40% more starfish that were found with machine learning, and all of those have been checked by humans, and we agree that the machine was correct in classifying them that way. We did actually do an additional tow in a slightly deeper transect on the sort of northwest corner of the reef on another day, and an additional 30 or so starfish were found there in a little bit deeper water. So it's even higher density than it might appear at first glance. And it just illustrates the flexibility of the system to go into habitats where regular manta tow might not be feasible. Okay, Brent.
So I'll just sort of quickly run you through this. There's a starfish sitting right on a bit of nice plate coral, and it's very obvious, the kind of thing you see. But there's a funny couple of things about the way the human brain and eye works, and that is you're drawn away from other objects in the same frame. The other thing is sometimes these things happen so fast that you can't see them now. I don't know how many of you saw it there. I'll slow it down, try it again slowly. There's the starfish on the right-hand side, right there, middle of the screen. It was visible for around about 6 frames. So that's less than half a second. We're frequently finding crown-of-thorns that are only visible for less than 1 second. This graph basically has the duration of visibility across the bottom of the screen. And since we're doing 15 frames per second, anything below here is visible for less than 1 second. Now, we have found starfish which are visible only for a single frame. In other words, there was only a 66 millisecond window of time in which that starfish was able to be seen, and they were seen. But the point here is that a great majority of these starfish would only be seen by a human observer if you happen to be looking at the right spot in your field of view at that time. This kind of 40% of starfish sort of visible for less than 1 second type of thing is actually, history will tell whether it's a coincidence or not, but it is uncannily like the amount that Russ and I missed when we were annotating all of our video footage. It's if the ML can do that and hit 40% more than an observer taking a lot of time to do it, then there's a great potential for that ML to in the longer term and over many sites take over from where humans are doing their observations and struggling with all of the things about concentration and scan rate and tiredness and things like that. Very early on, our first model began to find starfish that we had missed. And it's quite interesting, the process by which that happens. There's the starfish down there. Don't know how many of you saw it in that frame. In reality, the computer missed it in this frame here, detected it here, missed, and detected again. And this highlights one of the really nice things about using oblique fast frame video, in that we can build algorithms now which don't rely on a single detection, but rely on the pattern of a sequence of detections. In this case, the starfish was only visible clearly to the ML for 3 frames in a 5-frame sequence over around about 1/3 of a second. Now, when I first looked at that sequence, I wasn't even particularly convinced. I had to zoom in hugely until I realized that what I was looking at was a piece of coral here with the starfish partially covered by it. And then I started ticking off the characteristic features. So it's around about the right size range. It looks round when it's on a flat surface, the central disc about 50% of total diameter, many individual arms, and you can see some of them here and around here, over here and here. The coloration pattern, and the final giveaway was when you zoom in adequately, you can actually see the spines on the edge of the arm. So Russ and I both reviewed this and went, wow, the ML is starting to work. Russ, over to you.
Okay, so one of the more recent developments in terms of the data that's been possible to be derived from these images is size of starfish. So that offers the potential to get some insights, or some quite detailed insights, in fact, into the dynamics of starfish populations on individual reefs and across many reefs that are surveyed on the GBR. So these size estimates were fairly crudely derived as a first pass by looking at the dimensions of the box that delimits starfish in those frames. Each frame is slightly different. So a median size was derived from that. And here you got the size distribution of the population of starfish that were found at Llewellyn Reef. And although the sample size is not huge, it's you know, 100 or more starfish, and it looks like there are several cohorts there of 1-year-old, 2-year-old, possibly 3 and plus in a year class starfish, and some that are even older. So it's quite evident that this outbreak on Llewellyn is not the result of a single pulse of larvae coming from some distant reef. Rather, it's been, you know, potentially multiple recruitments that have resulted in the population that we see there. So, you know, that's something that's been a bit of a question, an ongoing question in terms of understanding outbreaks. So just one demonstration of the type of information that can come out of this. And it's also information that's useful to control teams. So, you know, they're more likely to see the bigger starfish, of course, because the behavior of the smaller ones makes them harder to find. They're more cryptic. And that gives an insight into, you know, what kind of time, length of time, the amount of revisitation might be required to completely control the starfish on that reef. Okay. Other information that can come from the glider data, and this is really important, is information on coral cover or the benthic community structure on reefs. So, of course, we're not killing crown-of-thorns just for the sake of it. We're trying to control them so that we can protect the corals on the Great Barrier Reef. And in order to do that effectively and to demonstrate that effectiveness, we have to have good data on coral cover and composition. So the glider data obviously presents an opportunity to get a much better picture of coral right around the reef, being able to do away with small snapshots of coral cover and having to extrapolate to the rest of the habitats around the reef. So I guess the task is to try to automate that so that the data on coral cover can be pulled out at the same time as we're getting the data on the crown-of-thorns. So matching up starfish, the amount of coral, where the control effort is, really getting a picture of how everything is tracking in terms of the control efforts. So this is one kind of approach that's been applied using segmentation. I think Brett can talk you through exactly what you're going to see next in this video.
So this is a short video from the, it's actually from the back of Lamont Reef. Every 15 centimeters of forward motion, there's a new frame, and the frame is analyzed in its entirety for 5 or 6 classes of habitat there. You'll notice that in the far field of the image, where it's a little bit murkier and a lot shallower declination angles on the vision, that it's consistently getting things a little wrong. But as the glider moves closer, gets better visual you know, acuity in terms of its on-ground pixel size and that, and starts to get that you know, view coming into the vertical projection, things are a lot more consistent. We're in the process at the moment of refining a region of interest and defining that properly, optimizing it, and then be able to produce habitat estimates every 15 centimeters forward. The question will then become one of how do we aggregate that information at a useful management scale, and just to sort of put it out there, RIS surveys tend to be done within sort of 5 meters of an observer, which implies about a 10-meter spatial scale. So perhaps we aggregate this stuff up at a 10-meter spatial scale. But certainly it was obvious while we were in the boat and watching the live feed that things like areas which have recently been killed by crown-of-thorn starfish, you know, were an abrupt transition to higher coral cover, or you would anticipate issues when the coral cover started to decrease and dead coral started to increase. All of these things are now sort of available at quite a fine granular scale.
Yeah, and if I could just butt in there, it was, was really instructive to go around those reefs, looking at the video in the boat as it was collected, and see just how the coral cover and coral composition changed systematically around the whole reef. It's it's not just that you happen to look at one patch and it's different over here than it is over there. You really begin to get insights into how reef orientation and other factors play out with types of coral that are there, and potential food resource for starfish, and so forth. So there's a lot of applications of this data once it starts to come online.
So where are we at, and what are we doing going forward? So with respect to the standard things collected in COTS manta towing, we already have things working usefully enough that when we go back into the field, some of these will be embedded. Every one of them needs more annotations, in particular to deal with the subject of generalization from one environment to another, etc., one type of reef to another. And then optimization, validation, and some quite detailed work to both validate and characterize the glider's performance, and particularly performance relative to other manta tow and diver search techniques. Also to look at whether those characterizations are then habitat specific, and look at repeatability of the method, etc. With respect to scars, there's some the training sets already developed, and there's a few more annotations needed, and then we will start to characterize those models, but we're a little way from that yet. And number 5, visibility is an interesting one. We've put it on the back burner, not because it's technically challenging, in fact, probably the opposite. Understanding that manta tows are about trying to estimate density of starfish on a per square metre or a hectare basis. Obviously, underwater visibility and its limitations is something that should be factored into regularly to these methods. They tend not to be with a lot of manta tow work, but particularly using some fairly standard computer vision methods, we're able to work out the depth of our field of view from the glider, and how that changes as you go around a reef or through a patch of runoff, from a lagoon or something like that. So we're certainly going to focus in the foreseeable future on getting the standard crown-of-thorns survey variables down pat on the glider. But then, of course, there's a whole bunch of other interesting things that we want to start to push into, which we think that there's a strong management imperative for. Within a frame, we can see relationships, spatial relationships, distances and clustering, etc., between starfish and feeding scars. Then we can start to pull together information across multiple frames, whether that's, for example, mapping as well as size distributions to work out recruitment patterns, looking at habitat types versus size, to look at whether they're growth or habitat-specific growth rates or size distributions, and also taking the mapping outputs and the habitat outputs and starting to improve metrics on just how much of an impacted reef has been lost or is recovering. I think there's the nice thing about this data set is absolutely everything that comes off the glider is archived. And so we have a very interesting ability to go back and revisit old data and ask new questions of old data. That's something that's a bit hard to do with most of the other survey techniques. The other area that's quite fascinating with the glider from a what we observe in the field sense is the way it seems to open up some new opportunities for fish surveys. Everybody knows that as you're trying to count fish, the little ones disappear and the big ones come in and say hello. And that leads to biases, and it takes a lot of expertise and care to try and minimize those. We also know that when we do things like chuck a quadrant on the coral for a photo, that scares away the fish in its own right, and therefore it's very hard to characterize fish in these surveys, even though fish might be one of the best indicators there are around of reef health and recovery and things like that. So the glider's oblique view then allows us to see the fish before they start to hide in the coral, but also the glider at a total wingspan of about 760 millimeters. It weighs less than 6 kilograms. It has a tiny frontal profile, and it's not very scary to fish. And so if you were to look at the way these clouds of small fish ordinarily behave when a diver's moving through the water or a manta, and then look at the video footage, you're struck by how little the fish react to the glider. We also have techniques that allow us to perform calculations based on things like movement of pixels within images that allow us to do things like this, where we highlight the movement of fish in a moving video, and we're finding fish which are absolutely not obvious to a human observer who might be reviewing that footage. The uses of that, of course, are that it gives us a jump start on things like identifying and counting fish and segmenting them for further analysis. But it also leads into an area where we're using that optical flow to identify obstacles that improve the glider's flight path planning ability. But I want to point out one example, and this is Aberdefduff and a sequence of video frames. There's only 5 frames there, but those frames represent around about 1.3 seconds worth of video footage. I've manually labeled those, each of the Aberdefduff in there to as part of our training set. And we find that in the first, real observation of the fish as you approach this particular bommy, there were 45, and then, a few milliseconds later, 49, and then 44. But by the time we get to 1 second from the first frame, the fish are starting to disappear into the coral, and by the time the glider's approaching over the top of them, 2/3 of them have hidden. For a human observer, it would be almost impossible to do anything other than an estimate to the nearest dozen or 100. But with the ML capacity that we have aboard the surface computer, there's no reason why the glider can't be counting the number of fish in every frame. And I think that opens up some really interesting ways to characterize biomass and diversity other than the types of things that we commonly look at on the seabed habitat classes. And there's another area which is, I don't want to describe it as blue sky, because in fact there's a lot about this which is very old, just hasn't been applied yet. But imagine a system where we were able to look at risk to downstream reefs from the breeding potential of the starfish which we're observing at this point in time. So live 3D modeling being conducted from the glider while it's making identifications of starfish and attaching risk to starfish on an individual or cluster basis. Both risk to, certainly risk to the downstream reefs, but also flipping the question around and looking at where have these starfish originated from? So the forecast question, should we cull these ones or those ones if it meant a different outcome for high priority reefs in the downstream area? Or asking the question, wow, we're seeing a lot of starfish here, and yet we're not really sure where these ones came from. What does the computer say? Now, the thing about this is, within industry, particle tracking models have been around for a long, long time. They're always used when some oil has been discharged from a ship and people need to backtrack to see which ship it might have been, or for spill predictions for finding marine pests, where have they come from and where are they likely to propagate to, in the event of a loss of a person or a vessel. Queensland Water Police, for example, have been using these models for 11 years in an operational sense to every time someone's lost at sea. And so there are plenty of people around who provide operational modelling capability to support these kind of initiatives. And one of these emerging collaborations is with a group that's based here in Queensland that does this consistently. And they've already done some work with me to look at how they integrate that in the spare CPU capacity of the glider, and make the results available live to people who are involved with decision-making processes. And for example, they've recently run fine-scale 3D hydrodynamic models of particles tracked from, for example, this little box up there around between Hastings and Michaelmas and Arlington Reef. In this case, the same model's been run with source points in each of those. And in each case here, we're talking about a 2-hour spawning event, based on what we know of the starfish ecology and when they spawn and where they spawn in the water column, etc. And looking at a couple of specific release points on each of those reefs and where the high probability recruitment events are likely to occur. And you can see that, for example, and sorry, I didn't put many reef names on here, but Britomar seems to, be a favoured spot for where recruits could end up from a Hastings reef release. But if the starfish happen to be more prolific on Arlington, then you can see that Britomar cops far fewer, and the great majority of recruits would end up a little further south, around about the Bowl Reef and through to the back numbers area off Townsville. So this is just, I guess for us, this sounds almost bizarre or very, very strange that this kind of modelling could even be done in a live sense and looking at clusters of starfish or even individual starfish. But in fact, the technology is quite old, and there are people who are quite skilled and experienced at this already. And we've already worked out the model schema and data management schemas that would allow this to be updated, for example, with live East Australian current and weather information, forecast information, so that at any given time the information is available. And I raise this because, well, obviously because it's actually possible and maybe even implementable in the near term, but more in the sense that our ability to ask questions of our environment depends entirely on what kind of tools and metrics we have. And I think in that sense, this sort of fast glider with high computational power aboard opens up an enormous amount of possibilities that we really haven't thought too much about yet. And for example, we don't, at this point in time, our control strategies are about saving coral through direct predation. But in the future, it's entirely possible to see that at a certain time of year, you might actually change that strategy over to protecting the, preventing the next version of an outbreak by targeting, in this case, for example, not Hastings or Michaelmas this morning, but Arlington, because we know that we're approaching spawning and the higher priority reefs are somewhere else. So some interesting kind of possibilities there. And I want to actually reach out to anybody who's, found interest in this presentation and say that as we advance the tech further, we will be only ever dealing with a small fraction of its capabilities ourselves, and we will be inviting collaborations and joint ventures with other parties to expand upon capability in the system and to demonstrate different use cases, etc. The other thing I wanted to say is, thank heavens it's all archived, because anybody who wants to now go back and mine the data for sharks or sea snakes or squid, coral trout, spider shells, giant clams, other types of starfish, and any other things that can be seen in the video, can go back and develop models and identify things and map them. And as the data set builds over time, imagine the resource in a decade when all of these things can be mined back out of old data sets. So I just want to kind of wrap up and say, around about 3 years now of quite solid progress, seems to be a very good potential. It's already, we took 5 units up to Heron Island last July, only needed to put 2 in the water. We've spent a lot of time since then optimizing the design for moving it towards manufacture. We're a little ways to go yet, but it is certainly conceivable that within the next year or two, we will have multiple units able to be used by, under the supervision of this team, because they're still a little bit fragile. Unless you happen to know a Linux command line interface, you'll struggle to use it. But within the next year or so, we fully expect to be able to start rolling out gliders to people in either teams or other research capacities to operate them without a robotic specialist or a Linux command line specialist within your team. Some aspects of the skill sets of the gliders are deployable now, and some of that's being embedded ready for the next round of fieldwork. We're going to focus a lot ourselves, and we're hoping, of course, that there'll be support for optimizing and validation of the technique, and especially inter-method comparisons and characterizations of where and when it works and where it might be needing more work. And I think I want to say that what we really see here is, let's start with good, and good means, we might just, for example, be able to provide data on the crown-of-thorns use case with, for example, the standard manta variables, and extend that to great with some of these other very, very interesting superpowers later on. I'm going to stop screen sharing now. Russ, did you want to say anything else while I do that?
No, I think I might just wait for any questions and see what comes up there. Thanks, Brett.
Thanks, Russ.